Welcome everybody to the second edition of our online show TPRC Talks. My name is Aniek van Damme and my guests are Sebastiaan Wijskamp, Technical Director of TPRC, and Sebastiaan Haanappel, Managing Director of AnyForm Engineering. And today we will take a deep dive together with you into the stamp forming. And therefore we switched to the lab today to give you a live lab experience. So welcome to the TPRC lab in Enschede. Yeah, first of all, please come along with me because I want to introduce you to one of our stars today. Hey, Dennis. Hi. This is the real star of the show, right? What does it do?
Yes, this is the press, and this makes it all possible. It's a fully automated press, similar to what the industry uses for stamp forming. On the left here we have an infrared oven that's used to heat the material, and in the middle we have a hydraulic cylinder with a set of tools that shapes the material. In the end, it's possible to apply 200 tons of force to get a good part quality, which is a lot of force.
Yeah, impressive. We'll hear more from you later on. I would love to see that press in action, don't you? Well, here you go. In this live talk show, we once again invite you along into the world of the ThermoPlastic Composites Research Center and into the world of the thermoplastic composites. In our very first edition, we were so happy to see that many of you shared your questions for our studio guests. That's why we'd love to give you that same opportunity today. So if you have any questions for my guests here in the studio, please do not hesitate to share them through the Q&A, and I will make sure there's room answering them in the last part of the show. So let's move to the guests. The first one is the Technical Director of TPRC. You might recognize him from our first episode. Welcome back, Sebastiaan Wijskamp.
Thank you, Aniek. It's almost a new career.
Yeah, you would say so, yes. Sebastiaan, why did we decide to do a full show on stamp forming?
Yeah, so we could talk a whole day about stamp forming, but let's try to limit it to an hour today. So if you look at stamp forming, it was the first process with which thermoplastic composites were used on big scale. So I think for 20-25 years we've been forming thermoplastic sheets into parts. Hundreds of thousands of parts are flying. It's also the material is finding its way into the automotive industry in combination with injection overmolding. But now the time has come to take this process and the material a step higher. We really would like to move into the primary structure of aircraft, for example, to heavily loaded parts, to chassis in cars. And that means we need to understand better what we are doing and need more research in that field.
Sounds promising. Thank you. Our other guest, together with his business partner, he established AnyForm Engineering, a spin-off company in the composite materials market and a partner of TPRC. Welcome, Sebastian Haanappel.
Thank you.
Sebastian, AnyForm Engineering supplies software for the automotive and the aerospace industry. What kind of software is that?
Yeah, we develop simulation technology to simulate the composite forming process. And if you simulate it, you can see how a laminate deforms when you're shaping it into a part. And you can say then whether that goes all right or whether you get certain issues. And yeah, that we developed that as a complete independent software package, which is easy to use for engineers, actually. So that's what we offer.
Clear, thank you. To go a bit more in depth, Sebastian Wijskamp, what can we currently do with stamp forming? What is the state of the art?
Yeah, so basically you take a flat sheet of material, which is pre-consolidated laminate. These are fibers and polymer already joined, and the flat plate already has ultimate material performance. The world is not flat. We like three-dimensional shapes, so we are melting the polymer matrix, and so we can then fold or mold the material into a certain shape. So if we do this well, we retain the material properties that were already inherent to the plate material, and we can make very strong and lightweight products.
And how long does this process take?
So heating takes about 3 to 4 minutes, maybe 5, depending on the thickness of the material. Then the stamping itself is a matter of seconds. So we're taking this sheet and try to form it into a 3D shape just in a matter of seconds. A lot of different things are happening at the same time. And then we take about 1 to 2 minutes for the material to cool, for the polymer to crystallize, to obtain the material properties that we need. Yeah.
That sounds quite easy, but I bet it's not just as simple, right?
You need a big press, as we saw earlier, but not to scare people off. You can already start with stamp forming. If you have an existing press, small hydraulic press, you take a little oven, you take a pizza shovel or another manual tool to transfer the hot blank to the tool, and then it's quite easy in essence. Yeah.
Clear. Well, just take one step back. Why is the increase of using thermoplastic composites so important?
So, in the end, we would like to make aircraft, for example, lightweight. So that means modern aircraft contain over 50% by weight composite materials. Now, usually these materials are made, parts are made, taking a very long time. For example, the curing of a thermoset oven material in an autoclave oven might take 1 day. With thermoplastics, since we only need to heat, melt, and shape the material, we can process very fast. And that means that allows us to even implement more composites in aircraft. And lighter aircraft mean less CO2 emission during the lifespan of 25 years of an aircraft.
True. Do you want to add something to that, Sebastian Haanappel?
Yeah, no, not really. I think it's in the end all about minimizing weight and reduction of CO2 emission. So, and the composites, well, with composites we can design lighter parts, right? So, yeah, and actually, like you say, we do this for years now, but yeah, the material has more potential in it. We can further minimize weight and minimize energy in the end. So, yeah, we only need to design everything a bit smarter, the parts and the process.
Mm-hmm.
Yeah, and a bit smarter means so we've been doing this for a long time, and we have really made big steps. But if you want to optimize the last 10, 20%, you have to put in even more effort than we have up till now. So shaving off these last bits of weight will take more and more research.
Mm-hmm. Clear. Yeah. And so it's time for stamp forming to go to the next level.
Yeah.
What does that mean for an engineer?
So that means that we're considering a huge variety of different parts that might be candidates to become a thermoplastic composite part. And to do that, you have to think of your design, but also on manufacturing. And these are very strongly interlinked with thermoplastic composites. So with composites in general. But with thermoplastic composites, you have to have a new mindset. So you can't just design a part, say, okay, fibers go in this and that direction. I need a certain material thickness there, and maybe I can work with a thinner part there. But you have to take the manufacturing process itself into account. So you need to know your processing during designing. You can build up this knowledge by doing a lot of trial and error. So you start with a certain blank, you go to the press, you stamp it, you find out something's wrong. You take the tool back to the tool shop. If you're lucky, you only have to remove some steel from the tool. If you're unlucky, you have to make a new tool. So that's on the manufacturing side. You might even have to discuss again with the design engineer, which can be in a different department or a building. So these iterations take a long time. And you really want to minimize that. And simulation software can really help you to design very fast.
Well, that's where your software comes in, right, Sebastian Haanappel?
Yes, correct.
Your software provides insights into the behavior of the composite materials. What benefits does that bring to the industry?
In the end, the benefit is that you obtain less trial and error using simulation tools. If you just forecast things, you know more or less already what will going to happen. So you can anticipate that on that. To give you an idea, if you do practical trial session, like Sebastian just mentioned, in the lab, you make your molds, you have your equipment there, it all costs money, you have the labor, the material. Well, ballpark numbers, such a trial session will cost you around 15,000 euro, can be a bit less or way higher, more, I think. But yeah, if you need to take back the molds and do some modifications or even redesign your molds or redesign your gripping or handling system of the blank, you have again a new trial session you need. And the more trial sessions you have, the more this 15,000 euro adds up. It becomes a multiple. And if you use simulation and forecasting tools, even if you just reduce the number of trial sessions by 2 or 3, it really saves you a lot of money already. So that would be the real benefit, I think.
But I also think that a lot of the design guidelines, the rules are already in the software. So the elements that you can use are there because of the experience of others. So the material cards in there, we'll talk about that later, I guess, they already describe what's happening during forming. So maybe it limits a little bit the creativity, but it's also preventing you from trying all kinds of different things that others already have done.
Mm-hmm. I see you want to react on that?
Yeah, well, we have quite some tool set in the software which you can utilize to play around. And furthermore, it just really helps that you can already see really what happens with the laminate, because in reality it's more or less a black box. You cannot really see what's happening. Behind your computer, you can make invisible the tooling and you can really see what's happening. That's quite convenient. Furthermore, it really can help you to assess what challenges an engineer will face when you do a process implementation. It really helps you to assess the project risk. And also, if you have some footage of the process simulation and you're working in a team, a structures team, for example, doing the stress calculations, and a manufacturing team, and one says, hey, I have a little problem here, then this tool can really help you to communicate the problem. So
next to the cost savings, it has more benefits, like better communication within the team.
Yeah, absolutely. Yeah.
Okay.
But I think we also can add that it's you can actually do things without simulation. So there are companies that have been doing stamp forming for a long time based on craftsmanship. And that's good. I think but if you're new in the business and you want to start stamp forming, then I think it's a good step to start with simulation as well.
Yeah. Well, Sebastian Haanappel, you brought a video that shows how the simulation process goes.
Yes.
Can you tell us during the video what we will see?
Yeah, let's have a look. So this will be about a certain part design in CAD software. Like most of the visitors are familiar with. So here we have that certain part design, and we need to make it somehow. So an engineer designs this kind of mold surfaces, for example, and we need to export them in order to do a process simulation with this. So this is our software. Here you import the mold surface, and you can further model the process. And one of those things are adding a material card, namely that describes the material behavior. And we can scope and play around with the process. So here we just use a quasi-isotropic layup, and we do a simulation. We also can design a gripping system, because you need to secure the blank somehow. And then you do a simulation. And let's have a look. Well, we got this, and it gives you already good insight of what will happen. It's well, we got quite some wrinkles here. It will be quite difficult to get a nice part out of this, but we have a virtual tool so we can play around. So we can, for example, play with the layup, make a cross-ply of it instead of a quasi-isotropic, and just see what happens, how you can influence the process. So here you see it goes already much better, and we only have one little wrinkle there in the corner. And that has been verified in practice as well. We can further optimize with a tool to play around with. So we can play around with the gripping design. Instead of one tensioner, we now put two in a corner. That's just to promote the shearing, which you need to avoid wrinkling. Do a simulation again, and there we go. We fixed that little problem there. And yeah, this shows you just how you can play around with a simulation tool and see what the possibilities are. And this one, yeah, we did this in practice as well, like you've seen in the earlier footage. And yeah, we really made a nice part out of it using this handling configuration with a cross-ply layup.
And there you have a beautiful fruit basket.
Yeah, it is.
Great.
Very lightweight. Yeah.
Well, to summarize what we just saw, why are extremely accurate simulations so important?
Well, in the end, the closer the predictions are to reality, the better an engineer can direct and steer modifications in the part design and the tooling design. So the earlier you got to the end point, the less trial sessions you need, and in the end that will just save you time and money, and not the least frustration too, I guess. Yeah.
Yeah, when it comes to communication within the team.
Yeah, too, but also when things don't go right in the first time, yeah, it can lead to some frustration, of course.
Yeah, I can imagine. Yeah. Well, what do you need to further develop stamp forming, Sebastian Wijskamp?
Yeah, so majority of the parts flying at the moment are based on fabric reinforced composites. So we've got some examples here. These are clips connecting frames to a fuselage, for example. And we like fabrics, and they're like the cloth of your clothes, very coherent. When you have this molten blank at 400 degrees Celsius, it tends to sag. But due to the coherency of the fabric, you maintain the structure. You can almost throw the blank onto the mold with your pizza shovel. So it's quite easy, we like it. But fabrics make the fibers undulate. So there's a little wave in the fiber, and that means that we're not fully exploiting the strength and stiffness of the fiber.
Yeah, thankfully we have another type of fibrous reinforcement in blanks, of course, the unidirectional composites, and they really help you to have a higher specific stiffness, and that means you can again create lighter parts compared to fabric parts. Because of the fibers run straight and parallel to each other, you increase the we call it the specific stiffness. Yeah.
Can you show that? You brought
well, with unidirectional material, they usually come in the form of tapes. You can actually use the automated fiber placement, automated fiber placement technique to deposit tapes only at the locations where you need that stiffness, because the stresses are higher, for example, in those areas. And in that way, you can really create a nice tailored blanks with local reinforcement, local thickening, and you can really direct the steering. Use a stiff in that particular direction, a certain stiffness where you really need it.
So this technology was not available 20 years ago. So that's why we started with the fabrics. So also the evolution of robotic manufacturing processes have helped us to go to this into this direction.
Yeah, and the material really made a difference here.
Yeah. So that I mean it's having the new automated processes, the simulation software enables us to move into this direction.
Yeah, it really makes a difference for the industry eventually, right?
Yeah.
It's very clear that you work closely together. But Sebastian Haanappel, why are you a member of the TPRC consortium?
Yeah, well, it has multiple reasons. First of all, it's a very nice consortium that brings together composite processing specialists. And yeah, we're of course most interested in the forming specialists from the industry. And yeah, in this platform we share our common challenges actually. And from that we can quite easily distill and hear what the current needs of the industry are and where they develop to, like going towards these tailored blanks and what are all the challenges there. So that's one of the reasons why we remember being part of this community really helps to improve or direct our own technology roadmap because we hear very well what's needed. And secondly, well, to make our technology better, we really need to do some fundamental research, but we don't always have the capacity to do that actually. And we need to study more the material behavior to make the predictions again more accurate. We cannot do that on our own, so thankfully the TPRC can do that, and all the members together can more or less direct the research. TPRC listens what's needed in the industry, and as a result, yeah, we can benefit from the research here, which we cannot do on our own. So that's the second reason, more or less.
Yeah, so it's added value both sides ways.
Yeah, I think for the consortium, it's good that this scientific knowledge is exploited through a commercial software package. Yeah. Otherwise, as I think I said last time, the knowledge ends up in a dusty drawer at the university. PhD students finish their work, write a thesis, then leave. And now the code gets implemented by experienced programmers at a company like AnyForm. And this programming usually is not the main interest of a PhD student. Yeah. So I think it's a win-win situation.
So every research that happens here has a link to the industry.
Yes.
So let's talk to two other partners. The two partners that will join are David Leach from ATC Manufacturing and Peter Bohr from DTC, that's Dutch Thermoplastic Components. They will join digitally, and I'm happy to hear their perspectives on how they work together within this consortium. Let's see if we have the first one already. Yes, hello, David Leach from ATC Manufacturing.
Yes, hello. Good morning from here in North Idaho in the USA.
Yeah, great. Nice to have you on the show. You're Director of Business Development within ATC. Can you tell us a bit more on ATC in general?
Yes, ATC Manufacturing, or Advanced Thermoplastic Composites, is focused on the manufacture of structural parts and assemblies for aerospace and other high-performance applications using continuous fiber reinforced thermoplastic composites. We were founded by an aerospace engineer, and we've always been focused on achieving high performance and lightweight with rapid process cycle times. And our main fabrication processes are stamp forming, as we've been hearing about, and continuous compression molding, or CCM. We've got 3 CCM lines where we manufacture laminates, which we use in-house, and we also supply to the industry. And we also manufacture profiles using the CCM up to 25 feet in length, or about 8 meters. But our main fabrication process is stamp forming, and we've got 10 stamp forming presses in-house where we form parts up to 60 inches by 30 inches, or that's about 1.5 by 0.75 meters. We are a full production operation. We manufactured over 1.1 million parts per year. And just to put that in context, that's the equivalent of 1 part every 30 seconds, 24 hours a day, 7 days a week, and 52 weeks a year. I've got a couple of examples of some of the parts that we manufacture in production. We've just been hearing some aspects of that from Sebastian and Sebastian.
Yes, please show us, yes.
Yeah, sure. Just as an example, this is a circular oval-shaped frame, a structural frame, fabricated from the fabric materials. You might be able to see the weave style in here. But it's got a U-shaped profile with these various sort of joggles or steps around the flange. So this is quite a difficult part to form rapidly, even in a fabric material, and avoiding wrinkles and other defects. And we've been hearing about unidirectional tape materials. Certainly one of our strengths at ATC is forming of UD tape parts. So unidirectional tape, as we were hearing, gives higher performance and more design flexibility, but they're more complex to form. So this is a small rib, but it is a primary structural part. It is, even though it looks simple, it's quite a hard part to form. It has curved flanges, and these are sort of 90-degree flanges, so you have to get very good quality around the edges. And then these two surfaces here have to have very critical dimensional requirements because they have to mate to an aerodynamic surface. So again, quite a challenging part to form.
Yeah.
So that's a quick overview of what we do at ATC.
Thank you. And could you tell me a bit more about the benefits for your company of knowing the exact behavior of the material?
Yeah, certainly. As we were hearing earlier, thermoplastic composites have been used for quite a long time, certainly over 25 years, but the technology is still maturing. We've been fabricating parts and structures successfully for quite a long time. ATC's been in existence over 15 years. But a lot of the initial learning was based on more empirical approaches with kind of qualitative experience. Understanding the fundamental behavior is important in expanding the use of thermoplastics and providing the confidence and consistency for larger, more complex and more critical parts. There are a lot of variables in the rapid processing of thermoplastics, and by understanding those key parameters, we can focus on the ones that really affect the processing and the behavior. And from this, we can develop those quantitative methods to model the processing and do virtual forming trials before we ever sort of design and cut a tool or form an actual part. And using this approach, we can really accelerate development cycles, reduce risk, and give more confidence in the use of thermoplastic composites. And obviously, a good example is the AnyForm process modeling software, which we've been hearing about, which of course came out of some of the TPRC research and development work.
Clear, yeah, multiple benefits, as I hear you say.
Yeah.
Yeah. Let's talk a bit more about the TPRC roadmap. What value does the research have that TPRC is doing?
Well, as a small to medium-sized company, certainly the ability to leverage the TPRC collaborative research is valuable to us. Once again, we could not possibly envisage doing the scope of research that TPRC partners are involved with fully. And this is important to understand some of the processing science. The TPRC research really covers the underlying kind of fundamental science at what we consider technology readiness levels sort of 1 to 3. And so the different TPRC members like ourselves can take that basic understanding and apply it to their own situations. Examples of some of the specific projects where we've used the output of TPRC programs include aspects of thermal stability.
Could you please, Mr. Leach, name one example, one final example?
Yeah, sure. The thermal stability, effects of defects, and advanced forming, which all relate directly to our day-to-day processes.
Okay, clear. Thank you very much for your contribution, and goodbye.
All right, thank you.
Bye-bye. Our other partner is also manufacturing structural parts for the aerospace industry. They're being based in the Netherlands, and which ATC was based in the US, of course. Let's welcome Peter Bohr. I hope the connection is established already.
Yeah,
Peter Bohr, yeah, I hear you.
I hear you.
Very good. You're head of new technology within DTC? And
Yes, that's
here,
right.
yes, we see you as well. Hello, welcome on the show. Good to have you
Thank
here.
you.
Tell us about DTC. How long have you been working on stamp forming?
Yeah, well, since the foundation of DTC, that was back in 1998 by David Moulton, stamp forming has been our core business really, and actually it started even before, in the beginning of the 90s, with working on thermoplastic composites at university and a small industrial startup. So it's fair to say that we now have like 30 years of experience in thermoplastic composites, so almost from the beginning.
Yeah, that's quite some years.
Yeah.
And how are you looking at the use of stamp forming in the future?
Well, we see several new developments. So one was already mentioned. First of all, we see a shift from the traditional fabric-based thermoplastic laminates to UD tape materials, with new types of carbon fibers and polymer matrix systems, especially the low melt PEEK material has a strong push there. And secondly, the parts are getting bigger and more complex. So parts up to 3 meters in length are things we are looking at, and increased complexity like thickness variations, joggles, beaded holes. They are all expanding the opportunities of thermoplastic composites if you can beat these challenges. And I also have an example here of a part which I hope is possible to see, that you can see the thickness differences here.
Yeah, as long as you keep it in front of your sweater, that's fine.
Yes. So and then it's necessary to have a very exact location of your materials. So these manufacturing tolerances are getting tighter and tighter as well. And then last but not least, all thermoplastic composites, we are shifting more and more to load-carrying parts. So the demands on tolerances and absence of wrinkles and limited waviness and those kind of things are getting more important as well. And that's where the simulation comes in, and also increasing the complexity of the tooling. And we have in-house tool manufacturing, which is a big help there.
Yeah, great. I see both Sebastians in the studio nodding their heads to what you say.
Yes.
So in theory, you and ATC Manufacturing compete with each other, right? Both being manufacturers. You being based in the Netherlands and ATC Manufacturing being based in the US. How do you see that, and how do you cope with that, both being partners at the TPRC?
Yeah, you're right. We are competitors. I'm sure David is checking out all the equipment in the background now. But on our aspects, we can cooperate as well. And we don't discuss everything with ATC, and I'm sure they are not discussing everything with us. But the thing is that we will both benefit if the adoption of thermoplastic composites in the aerospace industry grows further. So to expand into more structural loaded parts, we definitely have to gain more background, in-depth know-how, and a better fundamental knowledge on, for instance, wrinkling and waviness. And for such topics, the TPRC is beneficial for the both of us. And as a matter of fact, these topics are not only relevant for us, but also to other part manufacturers, but also material suppliers and OEMs, of course. So the work on material properties and improved material models for better process simulation software is a crucial development carried out at the TPRC. So this definitely helps the entire industry forward.
Thank you very much for your contribution, and goodbye.
You're welcome. Thank you.
Sebastian Wijskamp, what would you recommend companies who also want to start with stamp forming?
Yeah, so of course, obviously, companies should become a member of the TPRC.
Of course.
That means having access to this research roadmap that we heard mentioning. So you can work with us on stamp forming. Later on, we'll have 2 of our researchers present their work. So you can help. You can steer that research. You have influence. Besides that, you get the other project for free. You can also come to us for a one-on-one.
What do you mean you get the other projects for free?
So becoming a partner means you have access to all the research projects at TPRC. So
Okay.
if you're specifically interested, if you would join just for stem forming, you would also learn about fiber placement, about autoclave processing, about joining, everything you need to know about thermoplastic composites. But yeah, we would also be happy to help you one-on-one on a bilateral agreement. So we can help you with a basic tool design. You can bring your own tools to our press. Say everything is possible there. And we have, over the years, also developed a advanced level training on stem forming, where we really go into the theory that Sebastian, for example, developed in his thesis. Normally it's a 2-day course with a lot of fun in the laboratory, working on the press, doing simulations, of course, nice sandwiches during lunch, dinner, etc., etc. Regretfully, that's not going to happen this year. So we've converted this to an online training, and we'll have the first first training on March 25 and 26.
Oh, that's very good news.
Yeah.
Yeah, so everybody block your schedule and join the class.
Yeah, just follow us on social media. Dates will be released there as well, and
Great.
also some links to sign up.
Great. Well, it's not only our researchers and our partners who are taking this consortium to the next level. Also, our promising PhD students are very active in this respect. You already briefly met Dennis Brands. He and his partner Rens Pierik work together at a research that's called Perfect. And in the next video, they will explain more about it.
Hello, my name is Dennis Brands.
And I'm Rens Pierik.
We recently joined the TPRC as PhD students and are both working on a project called Perfect, which stands for Press Forming Without Defects.
We both have a degree in mechanical engineering from the University of Twente. And during our masters, we became really enthusiastic about research on composite materials. After some professional experience in industry, we found our way back into research on composite materials with this project on stem forming.
I've worked at AnyForm for 4 years, where I've helped to develop composite forming simulation software, and I've learned about the value of combining research and industrial applications. In my job, I was teaching people how to use the existing tools. And that gave me the desire to learn even more about the materials and processes that we're working with, an opportunity that I now have through this research project.
In our research, we focused on unidirectional materials. These materials gave more design freedom for the engineer, as you can make, for example, tailored parts, but it also allows for automated layup processes. Furthermore, it comes with better structural performance.
One of the challenges faced by manufacturers is the occurrence of wrinkles that occur in the very short time that the press closes. These wrinkles are not good for the final part performance, and hence we would like to minimize them as much as possible.
The relation between part design, process design, and the occurrence of wrinkles is not as straightforward, and this can really be a struggle for industrial manufacturers. Luckily, we've got process simulation tools, and with that, we're able to predict what occurs during the stem forming process. We're then able to modify the design on beforehand. With these process simulation tools, we enable industry for first-time right manufacturing of composite parts.
In our research, we try to improve the wrinkling predictions by measuring and describing the material behavior even better. For that, we're conducting controlled experiments to measure how difficult it is to deform the material when it is molten.
For example, I'm currently studying the friction between adjacent plies. We know that slippage between the plies is important to prevent wrinkling. From these controlled experiments, we now observe that there is a complex startup behavior. And we think that these transient effects are actually very important for our understanding of the formation of wrinkles during the stem forming process.
And I'm currently developing a new method to measure so-called in-plane shear deformation, which allows to extend the material over complex shapes. We measure the force required to deform the material at different temperatures and velocities to better understand the material behavior. Again, the in-plane shear deformation is required to form the material without wrinkles.
With the data from these controlled experiments, we try to develop constitutive models to describe the material behavior mathematically. With these material models, we're then able to predict the material response under arbitrary deformations that we didn't yet measure.
Which brings us back to the simulations. Material models are an important aspect of this simulation and how it's capable of predicting the deformation in any stamp forming process. By improving the material models, we're improving the prediction of the forming behavior, and we're also improving how it predicts the wrinkles.
Here at the TPRC, we've got this fantastic opportunity to work with the entire chain, from the start of material characterizations up to real forming experiments with the press standing here. These experiments can then be compared with simulation predictions.
Also, the feedback and discussions with industrial partners are an invaluable aspect of TPRC that really adds value to our research as well as our experiences as a PhD.
We also get to work here with a fun group of young and talented researchers, and we're all very enthusiastic about working on the future of thermoplastic composites.
In the end, we hope that our research on stamp forming simulations will lead to better and easier manufacturing of thermoplastic composite parts, perhaps even enabling more complex parts for more demanding applications in the future.
Yes, Sebastiaan, both Sebastiaans. What do you think of the work of Dennis and Rens?
Yeah.
Who wants to go first?
Well, yeah, I know these guys already a bit. And yeah, I really like their approach to bring our knowledge one step further. Their approach feels quite solid, quite good. Yeah, and I think it's quite a lucky shot that they can work together on such a complicated topic. I know from experience with my own PhD topics in the past, it really helps to have a partner in crime, so to say, to discuss each other's headaches, because this stuff is not easy. Yeah, I'm sure these guys will deliver something nice in the end. Yeah.
Great. Do you want to add something?
Yeah, it's good to see them happy still. Let's talk to them in 3 years, when they know what they don't know.
Because when you do a PhD research here, you do that for 4 years.
Yeah. So, and general trend is first year is exploring, discussing, defining the project. Then you have about 2 years to do some actual work. Then you have to deliver and write, and then the fun is over. But we're really confident that they will deliver something, as Sebastiaan said. We really need this fundamental understanding. It takes 4 years. We could really use the tools today, as we saw from our industrial partners. They are working on these highly loaded parts based on unidirectional materials. So I think they would be happy if they had the right tools already now. Yeah. We have to be a little bit patient. We feel the emergency puts healthy pressure on the researcher, makes the work really relevant. And I think on the lifespan of an aircraft, for example, we are happy to invest another couple of years.
Because then we talk about, what, 25 years? Yeah. What if somebody is watching and is interested of doing a PhD research here? What would you want to say to them?
Yeah, just reach out, find us via info@tprc.nl or careers@tprc.nl or via social media. Send your CV and we'll have a serious look and see if you can strengthen our team.
Well, great. Sounds great. Well, in the meantime, during the video, I got some questions by a lovely assistant brought to me. So the questions which some of you sent in, the first one is from Mayul Ducros. I hope I pronounced it right. Why would you use consolidated TP panels instead of a stack of non-consolidated plies? Yeah, is that a good one for you, Sebastiaan Haanappel?
Yeah, perhaps for the both of us. So please add when. Well, when you stack different unconsolidated plies, you have the risk of having lots of air traps. That's my experience, at least. And if you heat the whole stack of loosely stacked plies, if you heat it up and form it at once, you have the risk of having lots of voids in between, and the consolidation of the neighboring plies will not be that good as compared to starting with a fully consolidated ply laminate. Yeah. So I think that would be the main reason for that. It's interesting though, because it can save you a step in the processing. But this is the major reason why it has not been done yet, I guess.
Yeah,
what do you mean? It could save you a step in the process?
Yeah, you don't have to make pre-consolidated panels. So you can start right off with tape material, for example. Yeah, so it takes away one step.
Yeah.
We get this question quite often, especially from people that start exploring thermoplastics. So deconsolidation in the oven is the problem. But when you consider you have this, even if you manage to melt the material and transfer it to the press without it falling apart, you only have this very short time of maybe tenths of seconds to consolidate the material, to drive out all the air that is inside. And this time is simply not there. So there's a physical limit to what you can do. Same as goes as for a non-impregnated fabric plies, for example. First, we talked about first making a laminate, cutting a blank, and then going to the press. This is an extra production step. But to try to stem form a not fully consolidated material is simply not possible.
Clear. Let's go to the second one. This question is sent in by Jose Dipa. What is the maximum pressure that can be applied during stamp forming?
Yeah, it really depends on the press you have. You can exert as much pressure on it if you as like you want, but in the end,
must be a maximum, right?
Yeah, well, in the end, the required pressure is determined by the consolidation you need to achieve in the panel. So I mean, flat panels you make with relatively low pressures already, between 5-10 bars. When you stamp form a part in the three-dimensional shape, you usually need higher pressures to, for example, mask away some little waviness, or at some point the tooling does not close that well because of a little thickness variation. Then you usually need much higher pressures. Yeah, I've heard numbers of 100 bars, which is an awful lot, but yeah, the material can deal with it.
Okay.
Yeah, but it's still very low pressures compared to injection molding or sheet molding compound, where you maybe go to 500, 1000 bar.
He added something to his question. What is the ideal temperature for stamp forming?
Mm-hmm. Yeah, also that depends on the situation, especially which material you use. The material has a certain processing range in terms of temperature. And that range there, the material's in its molten stage, and when it's molten, it's soft, and you can form it. You need to stay within that window and take care of the cooling down. Form it before it has cooled down too much, of course.
Yeah.
Some basic numbers is say up to 50 degrees above the melting temperature.
Okay.
And then tool temperature between melting temperature and glass temperature. There's some guidelines here.
Okay.
Yeah. And it's material specific, especially.
Yeah.
So not a simple answer.
No, it's
okay.
material.
Sometimes that's just it. The last question is sent by Raj. I hope I pronounced it right. Raj Shah. Have you tried stamp forming reinforced fiber cloth and UD tapes together for any particular product?
Yeah, I think there's many researchers and pilot projects where hybrid laminates have been tested. Yeah. So UDs with fabrics on top or not.
Could you share the result within 1 or 2 sentences?
Yeah, it's just as easy as stamp forming regular thermoplastic composite parts.
Okay.
The thing is, and there are a lot of. So I'm going beyond my 2 sentences. Okay. So, but there are already applications out there. So there's a quite recent application. It's a brake pedal for a car that is based on a hybrid fabric unidirectional laminate.
Yeah. Okay, so that's a concrete example for...
That's the way we like it. Just put the right material in the right place.
Yeah, nice. Well, there were many more questions to answer, and we are very happy to answer them one-on-one after the show. Right, gentlemen?
Absolutely.
Yep. Very good. Well, this concludes our second episode of TPRC Talks. I hope you all feel inspired. I sure am. So, yeah, when I heard you guys talking about simulation and stamp forming, and then I would say my own takeaway from this show was that once again we see the enormous benefits of technological development, such as foreseeing what will happen thanks to smart software. So thanks again for pointing out that.
Sure.
So Sebastian Haanappel, when it comes to simulation and stamp forming, what would be your vision for the future?
Here I have again multiple visions, I guess. But
choose two.
Yeah. Well, part of our mission is that we would like engineers to develop some kind of instinctive reaction when they design a composite part, like, hey, don't forget about processing. Do a process simulation to understand what you're doing and what you can expect. So we're halfway there with that mission, I guess. There are much more engineers that can benefit from simulations. Second thing is, we would like to see our tool to be converted in some kind of automatic advisor tool. Now we talk about the process of setting up a model and simulate it, and more manual things. Mm-hmm. Apart from the calculations, that's not manual anymore, thankfully. But so imagine if you have your part design in your CAD software and you get an overlay image which indicates what goes wrong and where, and maybe even suggests what you can do about it. That would be the future, I guess. So then in the background, some simulation already running, or we are collecting information from a database, from historical result, and combine them so that it goes more autonomous, so to say.
So that would be your dot on the horizon.
Yeah, that's what we're working for, yeah.
Great. Sebastian Wijskamp, looking back at the show, is there anything you would like to highlight?
Yeah, so I go along with Sebastian, and we've seen that with stamp forming, as we do it here, going from fundamental basic understanding to the real application and software using software, we're filling a toolbox. Stamp forming is one of the tools to do something with thermoplastic composites, and we really want to apply this approach to other processes like fiber placement, joining, injection overmolding, autoclave processing. So filling this toolbox to make it easy for engineers to work with thermoplastic composites.
Yeah, and there was something happening in March?
It's the course.
Yeah.
2 days, 2 afternoons probably.
With simulations.
With simulations.
Yeah. Great. Yeah. Very much looking forward to it.
Yeah.
I would like to thank you all for watching. And if you have any interest in further discovering the benefits of thermoplastic composites, then we are fully at your disposal. If you have any more questions, please don't hesitate to get in touch with the TPRC. So I would like to thank my guests, Sebastian Wijskamp, Technical Director of TPRC, and Sebastian Haanappel, Managing Director at AnyForm Engineering.
It was a pleasure to be here.
Nice. Well, of course, I want to thank our other partners who joined. Let me see. We had David Leach here from ATC Manufacturing, and we had Peter Boer from DTC, and of course our bright minds Dennis Brands and Rens Pierik. Thank you all for watching, and we hope to see you on board at the TPRC.